All right, so in this lecture, we're going to start on something called Mohr's Circle. Now, a lot of students get confused by this topic, and indeed, it is kind of, I don't know any other word to describe it, it's kind of weird the first time you see Mohr's Circle. However, it is very useful, and it provides a graphical means of showing the stress transformation equations. So let's write that down. So that means we don't have to memorize any of those equations that we talked about in the previous two lectures. If we know Mohr's circle, we can have a better grasp of what's going on in a stress state than just by applying these equations. And that's why it's still taught today. So Mohr circle was developed by a German engineer, Otto Mohr, I believe sometime in the 1800s. So it's been around for a while. And there's a couple ways you can use it if you're very precise and use protractors and compasses and all that. You can use graph paper and look at the values completely graphically. But the way that we're going to use it in this course is a semi-graphical technique. We are going to use a couple of equations, but they're very easy equations and ones that I guarantee that you already know from other classes, like the Pythagorean theorem and the definition of a tangent and how to read a plot. So those things are all pretty straightforward. So let's see how we get to a circle out of our stress transformation equations. What I have written down there for sigma n and tau nt is our stress transformation equations, where I've used the notation sigma average to represent sigma x plus sigma y. So sigma n is equal to sigma average plus the quantity sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta, where sigma x, sigma y, and tau xy are the stresses in our original coordinate system, and the angle theta is some variable angle theta, which we can use to get to any particular orientation of a coordinate system that we want. For example, the n in the t direction or the x prime and y prime direction. The next equation is for tau nt, the shearing stress off at any arbitrary angle. Tau nt is equal to minus sigma x minus sigma y over 2 times sine 2 theta plus tau xy cosine 2 theta. What I'm going to do first to get a circle out of all this mess is I'm going to rewrite these equations just slightly. I'm going to put all the functions of theta on the right-hand side, and I'm going to put everything else on the left-hand side. So I have sigma n minus sigma average is equal to those functions of theta, and I have tau nt is equal to those other functions of theta. The next thing I'm going to do is I'm going to square both equations and add them together. And I'm going to go ahead and do this here on the paper. So I have sigma n minus sigma average, quantity squared on the left-hand side. And even though it's minus 0, there's a reason why I want to leave that in there for now. I'm going to put tau nt minus 0, quantity squared. And then over here, I'm going to lead off with the term sigma x minus sigma y over 2, quantity squared, cosine 2 theta squared, plus I'll have the cross term. I'll have 2 tau xy's, sigma x minus sigma y over 2. I'll have a sine 2 theta and a cosine 2 theta. I will have as my last term tau xy squared sine squared 2 theta. The next term, it starts with a negative, but when I square it becomes positive. So it looks very similar to the first term. Sigma x minus sigma y over 2, quantity squared. But now it's a sine squared 2 theta, but my cross term is negative, so minus tau xy, sigma x minus sigma y over 2, and I have a sine 2 theta and a cosine 2 theta in that term. And on my last term, I have a plus tau xy and a cosine squared 2 theta. Now the middle terms annihilate each other, they cancel each other out. And you have these terms here with have a sine squared and a cosine squared. And this term, the tau xy squared, has a sine squared and a cosine squared. Of course, sine squared 2 theta plus cosine squared 2 theta is equal to 1. So what I get left with sigma n minus sigma average, quantity squared, plus tau nt minus 0, quantity squared, is equal to sigma x minus sigma y over 2, that quantity squared, plus tau xy squared. All the functions of theta have gone away. All right. And if you remember from when we talked about this previously, the hypotenuse of the triangle that I constructed to come up with my roots for sigma p1 and sigma p2 was this term squared, or the square root of this term. So in other words, what I'm trying to say is that this is equal to r squared. And you may know that an equation of a circle has the form something like x minus x sub c quantity squared plus y minus y sub c quantity squared is equal to, well, let's call that little r squared. So both of these are equations of a circle. Now when we look in the x and the y-axis, x sub c, y sub c are the center of the circle. For us, we're not going to use x and y axes, but we're going to use sigma and tau axes. And so the center of our circle is going to be located at sigma average, comma 0. And our circle will have the radius capital R. All right, well, let's think about some of the implications of this on the next page. All right, so this is a graphical representation of stress transformation equations. I'm going to use symbols for now and try to explain this, but I will go through a couple of examples in this video, and I'll probably make a separate video at a later time going through some additional examples. In my class, this is a very important topic, and we spend a lot of time on this, and it definitely shows up on exams and final exams. So here's my stress state that I have, my x and the y. Stress is sigma x, sigma y, and my shearing stress tau xy. Like I said, symbols for now. I can locate the center of my circle on my sigma and tau axes, kind of like my x and my y axes. But there's going to be one distinguishing feature about my coordinate system that I'm going to set up. I'm going to call positive tau downward. Now, you're probably used to a regular coordinate system where you have x and y. But in our Mohr Circle coordinate system, I'm going to use the coordinate system sigma and tau, where positive tau is downward. So be careful with that. Some books will say that you have a rotation that goes this way is plotted down there, and a rotation that goes this way is plotted here. Same difference. What they're doing that is they're basing it all off of the rotation of this stress component that's on the positive x face. If it rotates clockwise, that's counterclockwise, that's a positive shearing stress when it's on this face. Of course, if you look on the negative face or the perpendicular face, it rotates the opposite direction. Now, I find that those little arrows kind of confusing, but a lot of books will do that. So some things we know about our Mohr circle is that the center of the circle is located at sigma average, comma 0, and that it has a radius of capital R. Now I'm going to try to draw in a circle. I may have to move the center of my circle if it doesn't look good. Okay, as far as my circles go, that's not too bad. All right, so one of the things that we had talked about previously was the maximum principal stresses. So here's my point, the center of my circle, which is sigma average, comma 0. And if I want to find the maximum normal stress that I can have, my maximum sigma, well, that's the coordinate of this point right here. The coordinate of that point is sigma p1, comma 0, because it lies on that axis. Over on the left side, this would be my point sigma p2, comma 0. And by looking at this, if I know the radius of the circle, and we'll talk about how to get that in a minute, if I know the radius of the circle, the value of sigma p1 will be equal to the average plus the radius, and the value of sigma p2 will be equal to the average minus the radius. The way all of these points that lie on the circle work is that the first coordinate point in this pair is the normal stress, and the second value is the shear stress. Now remember when we talked about the equations that we derived for the maximum principal stress state, we said that we had 0 shearing stress in the principal stress directions. Well, the Mohr circle shows that automatically to us. Now, the way to think about Mohr circle is not as two separate points that move independently of one another, but we want to think of an entire diameter at a time. Okay, so this red diameter that I'm sketching in represents the maximum principal stress state. Quite simply, it's the furthest that we can get along the sigma axis in either direction and still be on the circle. One of the other things we talked about was the maximum shearing stress state. Well, the maximum shearing stress state is the biggest that we can get along the tau axis. And if I draw my circle right, that should look like it's right above and below the average, comma 0, my center point. Is the furthest that we can go along the tau axis. Let me put this in green. So this diameter represents the maximum shearing stress state. And the coordinate of the point down on the bottom is sigma average, comma r, and up here on the top, that's sigma average, comma minus r. Again, the first number represents the value of the normal stress at that stress state, sigma average for the maximum shearing stress state, and then the second point represents the shearing stress. The maximum shearing stress in the plane is r, the hypotenuse of the triangle that I drew a couple lectures ago, or the radius of my circle here that I have. Now, one thing that you'll notice is that the maximum principal stress state and the maximum shearing stress state are 90 degrees apart. That seems a little funny because we talked about the maximum shearing stress state and the maximum principal stress state being 45 degrees apart in the material. But remember, when we did our Mohr circle, we came up with the circle, we were doing manipulations on sine 2 theta and cosine 2 theta equations. So here is something very important about Mohr circle. An angle in the material corresponds to twice as much on the circle. Okay, this is a product of how we came up with our equation for the circle. So the other thing that we want to say, and we'll tie all this together in a moment, is that every diameter of the Mohr circle represents a rotated state of stress. Okay, those are two important things. So the horizontal diameter represents my state of principal stress. The vertical diameter represents my state of maximum shearing stress. And there's going to be some diameter that I can use to represent my starting point for my XY stress state. The risk of making this page a little bit messy, I'm going to go ahead and use this. Let's suppose that my original stress state was represented by this diameter. Now I'm going to call this diameter over, this point over here on the right, I'm going to call that my X point. I'm going to call this one my Y point. And just like my coordinate pair normal and shearing stress, this point has the coordinates sigma x, comma, tau xy, and this point will have the coordinates sigma y, but I need to put a negative sign in here, minus tau xy. My x and my y point on my material, again, those are 90 degrees apart, but they're spread out to be 180 degrees apart on the circle. So I'm plotting this x point as sigma x, comma, tau xy, and this y point as sigma y, comma, minus tau xy. Let me show you something here, how we can find the value of the radius of the circle, but I need to clean this page up just a little bit. All right, so here's my circle. Now, I like to start off with Mohr Circle talking about the maximum principal, maximum shearing stress state, since we have just talked about that, but you don't necessarily know what those numbers are until you start at the beginning. So to start at the beginning, to construct the Mohr Circle, what we want to do is we want to first plot 2 points, what I'm going to call my X point, which is sigma x, comma, tau xy, and my Y point, which is sigma y, comma, minus tau xy. So these would be the things that I would do to start off. And I would plot the center of my circle. I would connect a line that joins the center of the circle with the X and the Y point. And then the next thing I would want to do would be to find the value of the radius. And here's how you do that without having to memorize a bunch of crazy equations. Drop a vertical line down to your point. It can be on the left side or the right side of the center. It could be either one. This will work on either way. Since we're plotting this point in a sigma tau coordinate system, that distance that I have drawn in there right there, I'm going to call that distance h. That h distance is going to be the value of tau xy. It's going to be that magnitude. And the distance from the center of the circle over to this side of the triangle, not all the way over here to the sigma p1 position, but to this point right here, that distance I'm going to call d. If we look at that distance very carefully, the way that we can find a value for that distance d is we would go from our origin to our x point. That would be the distance sigma x. And then we would take away the distance from our origin to the center of the circle, which is sigma average. So this distance right here is sigma x minus sigma average. Okay, it goes right to this point right there. Maybe I need to scoot it over just a little bit. So the distance d can be found as sigma x minus sigma average. Well, I have constructed a right triangle, and by the Pythagorean theorem, sigma x minus sigma average squared plus tau xy squared is equal to r squared. Now this doesn't, on the surface, doesn't look like the equation I had written down for r squared previously, but if you substitute in what sigma average is, you will get the exact same equation. So the point being, you don't have to memorize that equation for r squared. You just need to know how to read a plot. Once you have r, then the value of sigma p1 and sigma p2 are sigma average plus and minus the radius of the circle, as we talked about previously. Now the other thing that we need to do is we need to figure out the angle theta p to get to the principal stress state. Now remember, one of the things I said about Mohr Circle is every angle in the material corresponds to twice as much on the circle. So this is kind of like the triangle that I had drawn a couple lectures ago, where I had the angle 2 theta p labeled inside of it. And if I look at that, the tangent of that angle 2 theta p is equal to the height divided by the distance d. And that's the exact same equation that we had before, and just using some different symbols. Take the inverse tangent of h over d, if you got the numbers, divide that by 2, and now you have the value for theta p. All right, let me make a little bit of room, and we'll talk about sketching the principal stress state. Okay, so we want to sketch the maximum principal stress state. We've now gone through the process and we found the value of the angle theta p by looking at our triangle. Now here's something that's kind of subtle about Mohr Circle. The direction of rotation on the circle and in the material is the same as long as we have done this to our coordinate system where we have plotted positive tau downward. The entire reason why we plot positive tau downward is so this works out to be the case. And so what I mean by the sense of rotation is, look at this diameter that goes from the x to the y point. What we want to do, think of this diameter spinning about the center of the circle and clicking into the red diameter location. So we're going to take this x point and it's going to travel this way, and the y point is going to travel from its position this way. At the same time, it just rotates about, spins about this point. As I do that rotation, I'm going through the angle of 2 theta on the circle in a, a counterclockwise sense. So I'm going to come over here to my x-axis, and I go counterclockwise, but the angle is theta p. And I get to my principal stress state. Now in this particular problem, you see how this x point traveled to the sigma p1 location. That means the stress that used to point in the x direction is now the stress sigma p1. And at the exact same time, the stress that was in the y location travels this way to the position sigma p2. One of the things that the equations by themselves have a hard time sorting out, unless you're good at them, is which one is sigma p1 and which one is sigma p2. The Mohr Circle will tell that to you. It will give you that information. All right, so now we're on the red diameter, right here, the horizontal, and we want to get to the maximum shearing stress state. We have a couple choices we can make. We can continue on and click ourselves in from the red diameter into the green diameter position, or we can back it up and go clockwise from the red through our original position to the green diameter. Let's back it up and go the other way. So now we're going to take this and we're going to slide this diameter, we're going to rotate it about the center till we go this way. It's 90 degrees on the circle from the principal stress axis. It's 45 degrees in the material from the principal stress axis. The coordinate of the points tell us what our stresses are, sigma average, comma r. So I know my normal stresses are going to be sigma average. The coordinate up on the top is sigma average comma minus r. So on all the way around this stress state, I have sigma average. This is exactly the way that our stress state should look based on the equations that we derived. Now here's something that I think is the trickiest thing about Mohr Circle. We need to put the maximum shearing stress in the plane on this block. We know the value of the maximum in-plane shearing stress is the radius of the circle, r. But we need to know if the arrow will point up in this direction or if it will point in the opposite direction on that face. If you notice, I'm sketching in my coordinate system as I rotate my block. That's going to be very important. Look what happened to the x point. The x point started off with a positive tau because we're on the bottom side of the Mohr circle. I went and I got to zero shearing stress by touching this horizontal axis, and then I reversed direction and I brought that point down to the bottom of the circle, and I'm still on the positive side of the tau axis. That means I still have a positive shearing stress. Positive shearing stress points on the positive x face, and it points in the positive y direction. So this is the correct direction for that shearing stress. Once I have one of those figured out, the rest of these get penciled in for equilibrium. So the value of the maximum in-plane shearing stress is equal to r. Now, this is all in symbols, and I know it's kind of confusing with symbols, so I think it's going to be worthwhile for us to do a couple of examples with some different numbers in here, and I'll just make some numbers up. I'll get my calculator up, and we're going to do a couple things. We're going to do a couple problems where we find the values of the maximum principal and maximum shearing stress states, but we can also use Mohr Circle for the general stress transformation equations to find the stresses off at any angle in the material. All right, let me clean this up, and we'll do a couple examples next. All right, so for this example, what we're going to do is we're going to start with our stress state that I have sketched here. It's a plane stress state, and we want to find the principal stresses, the principal angle, and sketch the stress state in that new orientation. We're going to find the maximum in-plane shearing stress, the maximum shearing stress angle, sigma average, and sketch that stress state in its proper orientation. So when we do Mohr Circle, we want to start off with our coordinate system. Instead of x and y, we're going to have sigma and tau. And remember, positive tau is downward. We want to plot 3 points. So here's step 1. We're going to plot the center of our circle, which is sigma average, comma 0. We're going to plot the point sigma x, comma tau xy. We're going to plot the point sigma y, comma minus tau xy. So in this picture, my x point will be 50, comma 10. My y point is going to be minus 30, comma 10. And the center of my circle will be 50 plus negative 30 over 2, comma 0. That is going to be 10, comma 0. Now remember, if you have a compressive stress, that is considered a negative stress. So that's why my y stress was minus 30. I need to put a negative sign on this right here. My tau xy is positive 10, so that's why it plots as positive here, but I change the sign when I plot my y point. So the second thing I do is first thing I do is plot those points. So here's the center of my circle, 10, comma 0, and I plot my x point, 50 down the tau axis in positive 10. I want to label that and put the numbers there so I remember what they are. And then I'm going to put my y point on this. And I like to cheat this a little bit by drawing the line and then putting the dot, because otherwise I have a hard time getting things to line up. But here's my y point. It's going to be at minus 30, comma minus 10. And then we're going to draw a circle where this line that we just drew is the diameter of that circle. All right, it's hard to draw a circle on this writing pad that I've got, so I'll apologize for that crummy looking circle. So the next thing we want to do is we want to find the radius of our circle. If we want to find the principal stresses, we know that they're located here and here, the average plus and minus the radius. So I'm going to drop this vertical line down, and this distance is 10. And on this triangle, that distance is going to be 40. All right, here my x point was at 50, my center's at 10. The difference between those is going to be 40. And so what that says is r squared is going to be equal to 40 squared plus 10 squared. Let's see what r is equal to. I got 41.2. And the units of that in this problem would be KSI. So the values of my stresses, sigma P1 and sigma P2, is going to be the center of the circle, 10 plus the radius, 41.2, it's 51.2 KSI. Sigma P2 is the average minus the radius. It's equal to 10 minus 41.2. It's equal to minus 31.2 KSI. The angle that I need to rotate in my material corresponds to twice the angle on the circle. It's kind of hard to see it, but I wrote in 2 theta p. The tangent of 2 theta p, based on what's going on in that triangle, is equal to 10 over 40. So I go to my calculator, I put in 10 divided by 40, I take the inverse tangent, it's 14 degrees, and then I divide it by 2 to solve for theta p, and that is 7.02 degrees. The sense of rotation to align my x point diameter to my horizontal diameter is counterclockwise. So I come over to my x-axis, I go counterclockwise. It's not the scale. I go 7.02 degrees in the material to get to my principal stress state. My principal stress state, if you notice, my x point has traveled to this position, sigma P1. The stress that used to be the x stress turns into 51.2 KSI. And the stress that used to be my y stress turns into minus 31.2 KSI. I do not have any shearing stress. Next, I want to get to my maximum shearing stress state. That would be represented by the vertical diameter of Mohr's circle. I have 2 ways in which I can get there. I first went from my x point and my y point to sigma P1, sigma P2 diameter. I can reverse sense of direction and go this way. Let's do that first. In which case, I would go 90 degrees on the circle, clockwise, 45 degrees from the principal stress state in the material, clockwise, and I would have my maximum shearing stress state. Let me switch back over to my blue color. So for my principal stress state going this way, 45 degrees, I would have sigma average all the way around. And I would draw in my shearing stress. Now, the sign of the shearing stress, again, pay close attention to this. I started with a positive shearing stress, and I never crossed over the horizontal axis to the negative side. I'm staying on the positive side for these transformations. So I have a positive shearing stress on this block. Positive shearing stress points in the positive y direction on the positive x face. So that's equal to the value of R. Now sigma average, if we put the values in, let's see, that was 10 KSI. And R is equal to 41.2 KSI. Now we can go either way on a circle and get to the same point. Instead of having gone in reversed course, we could have continued on in the same direction of rotation. Let me try a different color for that. Let's see. Maybe this black will show up okay. So if you remember, the first rotation we did to get to the principal stress state was to go from our X point to the horizontal and my Y point to the horizontal. This diameter, think of that as a rigid stick or a bar spinning about the center of the circle. Now, if we would have continued on, I would have crossed over the sigma axis, gone 90 degrees on the circle. I would have gone 45 degrees in the material from the principal stress direction. So that would make a 90-degree angle with the shearing stress block that I just drew. This would be 45 degrees from here to here. The reference is from the principal stress axis. I draw in my square in my coordinate system. I know all the way around I have sigma average. That's not a big deal. But now look, when I started on the positive side of the tau axis with my X point, and I crossed over to the other side of the sigma axis, now I am changing the sign of the shear. You can think of the horizontal line as a sign changer for the shearing stress. So I'm crossing over. Now I have a negative shearing stress when I end up at this point. A negative shearing stress is on the positive X face, but it points in the minus Y direction, so it goes that way. Once I have one of those arrows figured out, the rest of those arrows get penciled in for equilibrium. And you should always draw all of those arrows. Now, you may say, well, one way I got a positive shearing stress, and the other way I got a negative shearing stress. Well, here's the deal. The material doesn't know what coordinate system you're using. The material feels the stress the way it feels the stress. But if we look at it carefully, the shearing stresses in kind of an absolute sense are pointing in the same direction. Let's look at this shearing stress on this top face of this. See how it's kind of pointing to the right? Look at this one. That is also pointing to the right. The point of this being, when you deal with stress transformations, it doesn't matter if you go clockwise or counterclockwise on your Mohr circle. As long as you're very careful with the signs of the stresses, if you keep all of them straight, you will get the same looking stress block at the end of your transformations. Okay, let's do another example just like this, but maybe a little bit quicker. And we're going to change things up a little bit and have our X point and our Y point be on the different side of the center of the circle. Sometimes that throws people off just a little bit. All right, so in this problem, we're going to do the same exercise. We're going to find the principal stress state and the maximum shearing stress state and sketch them in their proper orientations. So here's my starting stress state now. In this problem, I'm using megapascals. And instead of using the arrows in to indicate compression, I'm just using the arrows out with a negative sign. That's the same difference as putting those arrows pushing in. So when we start off our Mohr circle, we always start it off kind of the same way. We want to start off by plotting our 3 points. We'll start with our X point, which in this case would be minus 60, comma tau xy. Now if you notice, the shearing stress is pointing down on the positive X face. That makes that negative. We're going to plot the point sigma y, comma minus tau xy, which is going to be 100, and this is going to be positive 80. Then we want to plot the center of our circle, which is sigma average, comma 0. Now 100 minus 60, I should probably say that is 100 plus minus 60 over 2. That would be 40 divided by 2. That would be 20, comma 0. So the center of my circle is located at 20, comma 0. I'm going to sketch this in, and it doesn't have to be a really pretty sketch. If you have paper, it's easier than like I said, I'm drawing on this pad. There's my center of my circle. And then my X point is going to be minus 60. So I'm going to go this way, and I'll go minus 80, which is maybe this way. And I want to label that as my X point. It's important to keep track. I'm going to cheat that over and then draw the point. But that will be the location of my Y point, and its coordinates are going to be 100, comma, positive 80. Then I'm going to draw a circle that connects that diameter. I've already made fun of my circle before. We'll just leave it alone for now, but that's just the best I can do. All right, we're going to find the radius of the circle. We're going to do that by dropping down this perpendicular line. This distance is 80, and this distance is going to be 100 minus 20. That distance will also be 80. Okay, just kind of worked out that way. Here's R. In my right triangle, I've got R squared is equal to 80 squared plus 80 squared. Let's see what we get for that. 113.1. All right, so the values of my principal stresses are going to be the average plus the radius, 131.1. And we're going to have the average minus the radius, minus 93.1. Okay, the angle that I'm going to go to, get to the horizontal. Now, in this case, you notice I'm still going in the counterclockwise sense. If the points had plotted the other way, I would go in the clockwise sense. But the tangent of 2 theta p is equal to 80 over 80. 2 theta p would be 45 degrees. Theta p is going to be 22.5 degrees. And it's going to go clockwise. So that means I start from my x-axis. I go this way. (22.5 degrees). On this block, I have sigma p1 and I have sigma p2. Now I have to be careful. This is a very important point that I'm going to make. Here's my x point, and when I did my rotation counterclockwise, my x point traveled to this position, and my y point traveled to this position. Okay, now notice this y point is going to the position of sigma p1. So that means up here, the stress that used to be a 100 megapascals, used to be sigma y, now is becoming sigma p1, 131.1 megapascals. At the exact same time, the stress that used to be sigma x, minus 60, travels to this position, which is minus 93.1. If I have the arrows going out, then I can put the negative sign on that value. Okay, so let me say that again. This is really important. Here is the y stress, and it's traveling to that position. Here is the x stress, and it's traveling to that position. This position is the sigma p1 value, and this position is the sigma p2 value. It's the big value on the right, the smaller value on the left. All right, now to get to my maximum shearing stress state. That's represented by the vertical diameter of my Mohr circle. The coordinates of this point are sigma average minus r and sigma average r. If I continue on in the same sense of rotation, I'll change the sign of my shearing stress. Okay, so off of this, I go 45 degrees in the material. I have sigma average all the way around. And think about this for a second. On this positive x face, is the arrowhead on the top or is the arrowhead on the bottom? You pause the video and think about that if you'd like. Okay, let's figure it out. I started out with a negative shearing stress, and I crossed over to the other side of the stress axis. So I have changed the sign of my shearing stress. So I started with a negative, now I have a positive shearing stress. Positive shearing stress is on the positive x face, points in the positive y direction. Once I have one arrow, I can pencil in the rest for equilibrium. The value of this number is R. It's equal to the 113.1 megapascals. Sigma average is equal to 20. Maximum shearing stress state is always 45 degrees from the principal stress axis. It's either plus or minus. If we had gone in the minus direction, the block would look like this. 45 degrees this way. Now I want to caution you that a lot of books, what they'll do is they will take the difference between 45 degrees and 22.5. So they would probably say theta s would be equal to minus 22.5 degrees. And they define this as theta s off of the x-axis. Well, I know in this stress state, again, it's representing the maximum shearing stress state, I have sigma average all the way around. But in this case, I would have gone, let me try a different color. I would have gone first from my original y and x diameter to the principal stress, and then backed it up. I would not have changed the sign of my shearing stress. It stays negative, so it really goes in this direction. But once again, if you notice the arrowhead on this and the arrowhead on that one, on that face, they're both pointing in the same direction. Those two blocks are identical. What I would suggest is that for Mohr circle problems, that you first practice with principal stress states and maximum shearing stress states. And you take a look and you try different problems where sigma x is greater than sigma y, where sigma y is greater than sigma x, where you try one of these problems with tau xy being positive, and you try the same type problems with tau xy being negative. If you put in numbers and do all of those four combinations, there are no problems that I could give you on a test that you haven't already gone through the procedure. All this does, by changing the different magnitudes and signs of these normal and shearing stresses, is put your x point and your y points in different spots on the circle. Sometimes they could be here, here's the y, and here's the x. Sometimes they could be here's the y, and here's the x. Just depends on how those shape up. All right, we want to do one more thing with Mohr Circle. And I guess before I leave this section, I do want to say on my exams in my class, I will always ask on exam 3 to do the principal stress state and the maximum shearing stress state. We'll ask you to do that. I'll show you later the exact problem that I like to use, and it's on my website. But there's another way to use Mohr Circle, as we've talked about at the beginning of the lecture, and that is to find the stresses off at any arbitrary angle. I usually like to save that kind of question for the final exam. Now, I'm not saying that you won't have to find principal stresses on the final exam, but I am saying that you will have to find stresses off at an arbitrary angle. So let's use this stress state, and let's clean this up a little bit, and we're going to find stresses off at some particular angle off of the x-axis. Alright, so this will be the last thing we'll do in this video. We're going to use this stress state, and we're going to find out the new stress components off at some angle 10 degrees clockwise. Theta is equal to minus 10 degrees. We're going to use Mohr circle to find sigma x prime, sigma y prime, and tau x prime, y prime. So the way this starts out is exactly like we started out our Mohr circle for our other examples. We want to plot the center of our circle. We want to plot our x point. We want to label that, and we want to plot our y point, which is going to be 100, 80. We want to draw our circle. Or something that looks like a circle. All right. And we need to do a couple things before we can do a whole lot more. We need to find the radius of the circle. As we talked about, this distance is 80, and this distance is 80. So the radius of our circle, we had calculated from the previous problem, is 113.1. And we also need to find the angle 2 theta p. And we said that the tangent of 2 theta p is equal to 80 over 80, which makes 2 theta p equal to 45 degrees. Remember, we're plotting positive tau downward. Now, to find the stress components off at 10 degrees clockwise from where we started from, we need to understand that every diameter of Mohr circle represents some rotated state of stress. So this particular state of stress that I started with, my x and my y-axis state of stress, is represented by this xy diameter. We also need to understand that every angle of rotation on the circle is twice as much as that in the actual material. So here I am starting at this slanted diameter, and now I want to get to a new diameter. Let me put that in red. Still goes through the center of the circle, but the angle from here to here is going to be 20 degrees. Okay, it's important to notice that it starts from the xy diameter to the new, what I'm going to call the x prime and y prime diameter. See how going through that small arc, this x point changed into x prime, and this y point changed into y prime. Now, all I need to do at this point is to find the coordinates of that new location, and this will be sigma x prime, comma tau x prime y prime, and this will be sigma y prime, comma minus tau x prime y prime. Well, how do I do that? Okay. Well, I know the radius of my circle, and let me use a different color. If I drop a vertical line down, I can do it on either side. I know that this big angle in green, I'm going to call that angle alpha. That angle alpha, in this case, is 2 theta p plus my 20 degrees. 2 times the 10 that I had in this picture. So alpha is going to be 65 degrees. And if I know that angle alpha, then I can calculate the height of the triangle because I know what the radius is, the hypotenuse. So h is equal to r sine alpha, and this little distance d that I have here, that's going to be equal to r cosine alpha. So let's compute these numbers. It's 113.1 times sine of 65 degrees, and 113.1 times the cosine of 65 degrees. We have 102.5 and 48, 47.8. All right, now we're hit the center of the circle, and to get to my tau x prime y prime point, all I need to do is travel the height. But notice when I do my transformation, I'm starting on the negative side of the tau axis, and I'm going to this point, which is still on the negative side of the tau axis. I keep the same sign of the shearing stress as I started with. So this shearing stress, tau x prime y prime, would be equal to the height, would be equal to 102.5 megapascals, but it's negative. Let me make a little bit of room for the negative sign. Negative 102.5. Okay, did you catch that? The sign of the shearing stress started negative because it's pointing downward. And when I go through this 20-degree angle, I never cross over the sigma axis. So I keep the sign of the shearing stress. Now I had already drawn in that arrow pointing in the positive direction, so I need to include the negative sign when I write in the number. If I had waited, I could have drawn in the arrow in the actual direction, going down this way, and put the magnitude of the shearing stress. All right, sigma x prime. In order to get the sigma x prime, we have to be a little careful. It is not the value of d. What I have to do is I start from my origin, I go to the center of the circle, and then I travel back the distance d. So sigma x prime in this case is sigma average minus d, and by the same reasoning, sigma y prime is equal to sigma average plus d. Now, whether it's plus or minus depends on where your x prime and your y prime point land. If we had done a bigger angle, my x prime point could have been to the right of the center, and my y prime point could have been to the left. In that case, I would have had sigma x prime is equal to sigma average plus d, and sigma y prime is equal to sigma average minus d. Just have to be careful and see where the points land. You really have to use the plot to your advantage, be able to read the plot. So let's take this value. Sigma average was 20, and I take away the distance d, that would be 47.8. That would give me at minus 27.8. Sigma y prime would be 20 plus the distance d, be 67.8. All right, so if I write these on this block, I would write minus 27.8, and over here I would write positive 67.8 megapascals. All right, like I said, I usually ask that kind of question on your final exam. I'll make a separate video with a couple more examples at a later time. But the next lecture video that we'll have will be on something called the absolute maximum shearing stress in 3D Mohr Circle. Most books talk about 2D Mohr Circle first, which is what we did, and it's really the state of stress is a special kind of plane stress. But in the next video, we're going to talk about a more general state of plane stress called generalized plane stress.